Okay, welcome AP Chemistry students. This is a podcast on actually Chapter 7, which is Atomic Structure and Periodicity, and we're going to just basically be going over sections 7.1 through 7.4 today. So in this unit, we're going to talk about the modern atom, and prior to the modern atom, there was this dilemma of trying to understand from really the Rutherford model of the atom what is going on when we had that idea that, right, there's a nucleus in the atom and we're wondering like what the electrons are doing. This is from his famous gold foil experiment. Questions arose as far as what the electrons were doing. We know that electrons are negatively charged and the nucleus is positively charged, so why aren't those electrons being attracted into the nucleus? We know that things that are in a circular orbit lose energy, and why aren't the electrons slowing down, and why aren't they also collapsing into the atom? So these were dilemmas right at the turn of the last century, the 1900s, where people were wondering what in the world is going on with the atom. We didn't quite have a clear understanding. Okay, so there's some players in this, and this is actually the dawn of quantum mechanics. Prior to the 20th century, at the end of the last century, or now I have to say that at the end of the 1800s, scientists thought that they had physics all figured out. Actually, they were telling people not to go into physics because it was a dead science. And they believed that they had everything figured out as far as on our macroscopic world. They knew how to predict things. However, that story changed when we started looking at tiny, tiny pieces of matter, mainly the atom. It doesn't work the way it does in our macroscopic world, okay? And the dawn of quantum mechanics began, okay? So there was a big revolution, and it really was very exciting, really from the 1900s. Oops, let me go back to this slide. It really was from the 1900s to the 1930s. Our view of the atom changed pretty drastically from really still like maybe J.J. Thomson with the discovery of the electron all the way to the quantum mechanical model of the atom. Things changed. J.J. Thomson won his Nobel Prize for describing the electron as a particle, and his son George Thomson won the Nobel Prize for describing the electron that would act like a wave. And thus, lo and behold, came into the idea of the wave-particle duality. And you may know from, our first year course when we talked about that wave-particle duality, the thing that really explained that was the photoelectron, the photoelectric effect, which is what this PhET right here is simulating. And with this, you'll notice that you have energy here. You have a certain type of intensity. Well, we're just going to go up to like 55%, somewhere close to that. And I've got blue light, and the blue light is shining on this metal plate, and particles are being ejected out. What was unique and of this is that they thought that light behaved as a wave. So if light behaves as a wave, all properties of waves would exhibit this ejection. What happens is that when we go to a higher wavelength, okay, now we don't have this ejection anymore of the particles. Only thing that changed was the color of the wave and therefore the wavelength and the frequency of the wave. But now the particles are not being ejected, and that really was kind of troublesome for us. To try to figure that piece out. It was actually Einstein who figured that out with his famous photoelectric effect, and that's what he won the Nobel Prize for. And we're going to talk in a minute about what ramifications that it has and how that kind of all plays out with here. Okay. The other piece too is that in that dual theory of matter, the wave can act, or the electron can also act as a wave. And we're going to have, wave-like properties with that. And to show that, I want to highlight here for you guys this piece right here. So here's the second PhET that we're taking a look at. And this is a PhET that is just kind of the hydrogen atom. And I'm taking a piece of, or actually the light, I'm turning on the light, and you can see with this classical billiard ball Dalton view of the atom, you can see that light is not, it's kind of bouncing back. But in our classical piece, where you had an electron moving around the center of the atom, or you may even remember when we're talking about the Bohr model, you have the electron moving around. We're thinking of things and matter as being a particle. But in reality, matter can also be like this. It can be like a wave. This is a example of the de Broglie idea of how an electron could actually be, or matter could actually be part of a wave as well. So let's kind of get back to it here with this, what this really means. And to understand really particle behavior at this really small scale, we have to understand something which we call light, okay? Light is electromagnetic radiation that propagates through space as a wave, moving at the speed of light. And you guys should know that the speed of light, here I have it down here, is 3 × 10⁸ meters per second. And you should know that it's equal to the wavelength times the frequency. So they are inversely related. The wavelength, which is defined as the length of the wave from top to top, okay? So that would be defined as a wavelength, okay? The unit for wavelength in our course is typically in meters because the speed of light is in meters. But when we're talking about really small things, you're going to see it often in nanometers, which remember nano 9. So there is 1 × 10⁹ nanometers for every 1 meter. So you may have to do a conversion in there. This stands for frequency, which has a unit of hertz, which also could be a 1/2, which is what the wavelength would be, okay? So when we're talking about wavelengths, if you remember from your first year course, if you have a long wavelength, the frequency is very low or small. Whereas here, this represents high frequency, and notice how the wavelength is shorter. You would have a short wavelength, but you have high frequency. And these are also related by this equation, which you should know. The delta E, or the change in energy, is equal to h nu, where nu stands for frequency, okay, and h stands for Planck's constant, which is a number that I believe is on your gray sheet, and you should really kind of check that out as well too. I believe it's on your gray sheet, and if not, it's definitely in your textbook. You should take a look at Planck's constant if you ever have to use this relationship. This is also used in conjunction with C is equal to wavelength frequency, where if you knew the wavelength, you could calculate the frequency and then apply the frequency in the energy equation as well, okay? So answering the dilemma of the atom is to treat electrons as waves, and as the electrons move towards the nucleus, the wavelength shortens, therefore shorter wavelengths, higher energy. Higher energy means that there's a greater distance from the nucleus. And this was really brought about by a guy by the name of Bohr, and as we were kind of showing you Bohr's diagram of the atom. Bohr was trying to figure out really the nature of the matter, what the electrons were doing, and he did that by looking at a hydrogen gas, and he basically looked at it through a prism. And if you'll remember, he found 4 distinct lines, which we call bright line spectrums, that was really unique for hydrogen. And he had questions. He had questions about, like, what was all this black space about? Okay, what did this stuff mean? The fact that there was no line there. And then he also had the questions of what produced that line. Okay, if you will recall, they are happening because of energy shifts. Okay, so electrons transitions involves jumps of definite amount of, oops, that should say energy. Okay, and that is because the atom, he said, was quantized. And that means that the electrons could only be in specific energy levels. Depending upon the transition, depends upon the amount of energy that's given off. And that energy, if you would remember here, is equal to a certain frequency. And that frequency is related to a certain wavelength. And that is dependent upon the color. Now, we only see colors if that energy is related with a frequency which relates with a wavelength that's in the visible spectrum. Then we will see a color. But there can also be these transitions like this one right here, which is the Lyman series, or the Paschen series, that would either be in the infrared or the ultraviolet spectrum based on the amount of energy that is released. Okay? And if you will recall, this gives you the colors that you would see in flame tests. So we can identify the colors of these flames, like this would be strontium. Lithium usually gives you a bright red flame. Potassium, kind of a purpley flame. Copper, kind of a green flame. And these are all identified by the energy transitions that happen. And these are the colors that you see are typically the most prominent from these energy transitions. Now, the thing about the hydrogen atom, or about the Bohr model of the atom, which when we think about what the Bohr model of the atom looked like with the nucleus, and then we had said, oh, there's rings, and we thought that that would look lovely because it would be very much like our planetary model. Wouldn't it be cool if the outside world, the macroscopic world, was like the microscopic world? Well, it doesn't quite all work. The equation only works for atoms with ions with a plus 1 electron, which is really only these species. You may be asked, and you should know, how to calculate the energy associated with the electron in the hydrogen atom. This is an equation that is specific to hydrogen, okay? And in your homework as well tonight, you may be asked to calculate the energy transitions of a change in energy, okay? Which represents N, as you know, would represent the energy level you're in. So if it's N2 going to N1, what would be that energy transition, okay? So this is also in your textbook, and this lesson just covered 7.1 through 7.4. It was very brief. I highly recommend that you also read this section of the textbook and do the assigned problems. I wish you well and good luck.